of the Son, and of the Holy Spirit. Amen. Lord, grant us concentration that we may learn, listen, understand, have a peaceful mind, and remember that you're with us always. Amen. For this video, it's going to be as requested in our meeting the other day. This is a representation or a summary, if you will, of the material covered in the beginning of the coloration dyes and color considerations. And so it's not going to be the complete lecture that I gave in class, but at least hopefully give you some of the points that you can begin to look through your notes and have some backup information here. So we started this particular lecture talking about three terms, and these are important terms as we begin to think about and consider how we add color to materials, to fibers, even to think about this in terms of other methods of colorations. And so that is that a colorant is any chemical which is able to impart color on a substance, okay? And so I break these down into 3 points, 2 of which we're going to focus on in this part of the lecture. And that is, those are dyes, which must be soluble in a solution to allow it to be applied. And the dyes are going to get in and bind within the fiber itself. And so this is going to be found in the material. It doesn't sit on the surface, but it actually sort of incorporates itself into that. Pigments, on the other hand, are particles that are not soluble in the solutions. And so whatever we're using to apply it in, and so they remain sort of on the surface of the material. And so more what we're going to talk about in the rest of this lecture, and probably in the next video too, are going to be pigments. And so pigments or colorants are all around us. So what are some of the characteristics that would make a colorant a good dye? Well, first of all, it has to have an intense color. If it's sort of a moderate color or a low color, it's not really that great. So it must be able to react well with light. As we'll talk about in a little bit, it must be able to absorb light at particular wavelengths. It must be soluble in water. Well, why is that? Because during the dyeing process, we actually will have to have it suspended in water so that we can treat the fibers, the fabric, the yarn that we're going to dye. Reactivity with the fiber. Since it's not simply setting on the surface of the fiber or the material that we're using, but actually incorporates with that, it must be able to react to it, to bind in there, form chemical bonds, as we'll talk about and have presented with the mordants. These are going to be primarily ionic and hydrogen bonds. And lastly, it must be fast. Well, what we mean by fast or show fastness is that it must be able to be retained as a result of the dyeing process. So even if you wash the fabric or the yarn or the material, the dye itself won't wash out. And so it must be fast to be able to be considered that. I think a great way to start this was with the question, why are plants green? And hopefully you guys know, as we'll see in a second here, that's because the primary pigment in there is chlorophyll, and chlorophyll reflects wavelengths back that are green. Is green the only color present there? The big answer to that is no. Okay? There are a number of different pigments that are also present there that we'll talk about in a second, and some that you've seen when we did the dye isolation. And so what is the relationship? Well, in this case, the pigments are going to capture the light energy and use this to make chemical energy. And the primary, we could call this photosynthesis. The use of light energy to make that. And the primary molecule that we're interested is glucose. And of course, glucose is a carbohydrate that will be used in that. So what is chlorophyll? Okay, so chlorophyll, this is the molecule shown here, and we see two primary parts. We have the porphyrin head, and the porphyrin head is going to be where the light is actually absorbed to be used for photosynthesis, and a hydrocarbon tail. The hydrocarbon tail is going to be the part that sort of anchors it or connects it to the cell wall, to the cell membrane. Now the porphyrin ring is really what's important. It's the ring structure that's going to absorb the light energy. Okay? And so the key point here, and we'll see this in several different ways, are these double bonds as shown here. Okay? And we're going to see that in most of the dyes that we look at and consider, these double bonds are present. And that means these are going to be the regions or the areas that can absorb or interact with the light energy. And so they'll absorb certain wavelengths and they're going to reflect other wavelengths. Magnesium ion is in the center here. Metal ions are very good at transferring electrons. In this case, it's going to also assist in creating this structure. Okay? And the structure is important. This flat structure, sort of think of it that way, the flat structure is able to interact with more light as it hits. So the question that still remains is, how does this relate to color? Okay? And the answer to that question, we need to start with a little overview about light. What is light? Well, light is electromagnetic radiation. So that means that it's going to have a certain amount of energy that's present in the light. And so when we talk about light, it's important to keep in mind that what we consider visible light is only a small portion of all the electromagnetic radiation that's present there. And so light is both a wave and a particle. And that particle we refer to as a photon. Okay? And so it's going to move in a wave-like manner. So I'm going to draw a couple of waves here and talk about the difference here. All right, so light contains energy. The energy is what's moving the photon. And there's a direct connection between the wavelength, and so the wavelength would be from the top to the, or from the bottom to the bottom. And this is often given as the Greek letter lambda. It's not a very good lambda, so we'll try that again, okay? The Greek letter lambda. And the wavelength is what determines, or is going to give an idea of how much energy is present there. The longer the wavelength, the less energy. So if you'll notice on this figure below here, we increase wavelength from 0.0001 nanometer, very, very, very small, up to over 100 meters, which would be a very long wavelength. Okay? The relationship here is that as the wavelength gets longer, there is less energy. So there's less energy here, and there's more energy here. And so the electromagnetic radiation that is present, okay, visible light, what we would call visible light, is only a small portion of that. Or electromagnetic radiation that has a lot of energy, hence a very small wavelength, would include the gamma rays and X-rays and UV light. These have too much energy to be able to be captured by our eyes or to react with chlorophyll if we're talking in terms of photosynthesis. On the other end of this, we have radio waves. I always say this figure is missing one. Microwaves are out here too. The microwaves and infrared that have very much longer wavelengths and therefore have less energy. In fact, we could say there's not enough energy to react with the pigments such as chlorophyll. In this small range between 400 nanometers and 700 nanometers, I always round off to 700, gives me a nice area to think about this. In this range, there's just the right amount of energy to react with or interact with the particles that are present there. Okay, and so we're going to talk a little bit more about what it means to have just enough energy in a little bit. Before we do that, we're just going to go over again most of what is on this slide I've already mentioned, in that light is both a wave and a particle, long wavelengths, less energy, short wavelengths, a lot of energy. Okay. Within that small range between 400 and 700 nanometers, okay, roughly speaking, this is visible light. Okay. Now, visible light, and I think most of you know this, but just as a reminder, white light that we see all around us combines all of the colors together. They're combined into one light that we see. We can actually separate those out if we use a prism, which will allow us then to separate out into the various wavelengths and make a rainbow. When it rains out and the sun's out, that's when the light passes through those raindrops, gets separated, and we see the rainbow. And this results in the fractionation or the division of the light into the various wavelengths. When we talk about color, or our perception of color, we're going to break this down into three different changes or three different characteristics, if you will, that will determine how we perceive the color. Okay? That's the nature of the light. In other words, what type of light are we using to view it through? And if there's a limiting wavelength of light present, that may change the color as we perceive it. How the light is absorbed by the material, and again, this is getting back to that point of saying there has to be a certain amount of energy to absorb the light energy. If there's too much or too little, that light's actually reflected off and will be perceived by us. And the last thing is how our eyes themselves respond to the light. So we're going to take a little closer look at each of these three. Now before I do that, let's start with the nature of the light. And so when we talk about the nature of the light, what we mean by that is what wavelengths of light are present. Okay? So what wavelengths of light are present? And in true complete light, we would expect all the wavelengths to be present in equal amounts. And this is really only seen with natural sunlight, in fact, at noontime. Okay? Almost all of them are present at equal light. So natural light gives us the best and most complete wavelengths of light that are present there. In the evening, as the sun is setting, you'll notice, you've probably seen sunsets before, that the sky will begin to glow sort of a reddish, orangish color. That's because at that point there are less short wavelengths, that would be violet, blue, and green, and more long wavelengths, red coloring, that's present in light. Because as the light's coming at an angle, it's reflecting some of the light, especially the short wavelengths, are reflecting off of the atmosphere, and so that changes our perception of light. Best perception would be at noontime when there's equal amounts of wavelengths present there. Most of us don't live in natural light most of the time. We spend a lot of time in artificial light. So incandescent or traditional light bulbs, okay, this is going to be pretty poor, but that's a drawing of a light bulb. They have a little filament inside that's going to glow, okay? And it's usually made out of tungsten. When it glows, that creates the light. Well, incandescent light has a higher proportion of the long wavelengths, which means there's a slight reddish tint that will be present to that light. We perceive that more as an orangish tint or a yellowish tint because it's going to be in that range where most of the wavelengths are present. Fluorescent lights, on the other hand, are biased towards the blue. They have a higher proportion of short wavelengths that are present there, so it gives everything sort of a bluish tint to it. LEDs are interesting. I haven't included this on here, but the LED lights, we have the ability to change that. They're going to have varying amounts of color that are present there. And so our ability to perceive color is going to be determined by both the intensity, how bright the light is, and also the proportion of different wavelengths that are present there. So that's the nature of the light. So the second point was how the molecules are able to react to the light or absorb the light. Okay. And so I gave you on this slide a number of different dyes that we're going to come across before. Some should be familiar: indigo, which is a blue color. Okay. Carotenoids, beta carotene being the best example, which would give an orangish color. Okay. Some of them that you may not know, but actually you're probably familiar with. The anthraquinones will give a reddish color and absorb through that. And the flavones, we got a couple of different examples there, which will have more of a reddish or yellowish color to it. And notice in here that all of these molecules show one common feature in different way or another. And that's a double bonds between the carbons. Okay? And most of these are found right next to each other. Okay? I'm going to use carotenoids as an example. You'll notice you have a double bond, single bond, another double bond. Those are referred to as conjugated double bonds. And these are important because these conjugated double bonds are what provide the area to move or excite electrons. And that's really what is happening when the molecule is absorbing light. It's exciting, or it's using the energy in the photon to excite the electrons. If it's not able to excite the electrons, it's simply reflected off, and that's what we can perceive. Okay? And so this is, what do we mean by the double bonds? Well, I mentioned the double bonds already. The rings themselves are common. This is indigo. That's one of the anthraquinones that are present there. And these double bonds are going to be sites where we can excite the electrons. Well, what means an electron? So if we looked at an atom, okay, we would see that there's the center, which contains the nucleus. Okay, I'm going to put an N. And in the nucleus are the protons and neutrons. And outside of that are where the electrons are found. But electrons, the best we can describe it, don't randomly move around. They're going to be in certain shells, okay, or electron shells we could call them. And when energy is absorbed by an electron, if it can react to that photon or the light energy, the absorption of light is what's going to allow for the movement of the electrons. So as it absorbs the light, electrons will move out to another shell. Okay? And so that's what we're looking at on the bottom here, is our electrons are being shuffled out as they absorb light. So the energy that's in that particular wavelength, if it has the correct amount of energy, will cause it to move up to the next level. Okay? So it'll jump up one level. If there's not enough energy, okay, the electron pretty much stays where it is. If there's too much energy, then it's going to either come off completely, or the light itself will just be reflected. What determines whether the light's reflected or the energy is absorbed is going to be the shape of the molecules and the location of the double bonds. And so when we talk about the different shapes react with different wavelengths of light. And so depending on whether it can absorb the energy or reflect the energy, that's the color that we perceive. Okay? And so, for example here, the colors of lights absorbed in these different wavelengths are going to be the opposite of the colors that are perceived. So if the blue and violet light is absorbed, we're going to perceive it as a greenish yellow. So we could get philosophical and say, what color are plants? You would say they're green. I would say they're every color but green, because that's the color of light that we observe. And on the bottom here, we're showing absorbance, how much energy is absorbed at the wavelengths of light that are present there, moving from 400 up to 700. And so we can look at a couple of different pigments to see how light's being absorbed there. And so you'll notice chlorophyll A. Chlorophyll A is the dark green line. And so chlorophyll A is absorbing light in the blue spectrum and in the red-orange spectrum. So what it's reflecting back, if we combine those colors together, it's going to give us green. That's why plants are green. Chlorophyll B, which is very closely related, reflects a little more into the blue range and a little closer to that. And actually, because there's some purple that comes through, it gives it a slightly more bluish tint to it. So this is the idea of how colors, and when we talk about pigments, it's the same idea. If it's able to absorb the energy that's present in a certain wavelength, then that color won't be present, and then it will then reflect off the other colors. So how does this connect? So just as a side note, I think looking at the biology here, how does this connect to photosynthesis? Well, photosynthesis is the process by which the energy is turned into chemical energy. And so the wavelengths of light that are connected, that energy is used to excite electrons that can then be used as an energy source in the process of making molecules or making sugars. And so the light energy that is absorbed is used to excite the electrons, and that will allow it to use that energy then. In the case of our colorations, our dyes, that energy is typically not going to be used for chemical reactions, but the energy will be released as heat. It's not a lot, but if you think about wearing a dark color or a black sweatshirt on a very sunny day, you can feel some of that energy as it reacts with the dyes in there. All right, so I'm going to stop this video at this point in time. We're getting a little long, and I'll do a second part of review related to the response that we have and how we are able to perceive color through that response, and then talk about classifications of dye. So if you have questions about this review, please post them on the Schoology discussion board or contact Brother Marker I, and we will make sure you get answers